Hello and welcome to this video. In this video we're going to be going through the topic of semiconductors. So we've previously looked at ohmic resistors, filament bulbs and diodes in the VI characteristics. Now we're going to have a look at what happens if the material that we have is not simply just a metallic lattice, and that is what is formed with semiconductors. So we can split semiconductors into two sections or two components. The first one that we're going to talk about are thermistors, and then the one that we're going to talk about later is LDRs, or light dependent resistors. Okay, now these two types of semiconductors are really useful because they allow us to have a part of the circuit that's going to have some stimuli, right? So if we want the circuit to react to maybe high temperatures, and we say that if the temperature increases, we want this warning light to go off. Okay, we can use thermistors for that purpose. If we had LDRs, so like in street lamps, when the light intensity gets too low, we want a bulb to turn on. Okay, so these two things can act as essentially like sensors. Like thermistors would be in your kettle. As soon as you reach a high enough temperature, your kettle will stop boiling the water. So let's first look at thermistors, and then we'll see the similarities between thermistors and LDRs. So thermistors react to temperature. Okay, so they react to temperature. Now the general idea with temperature and resistors, as we've looked at in the VI characteristics video, is that generally if we increase, if temperature increases, it means resistance increases. Okay, and this is because all of the ions in this metallic lattice, when the temperature increases, they vibrate with much larger amplitudes, meaning it's much more difficult for the electrons to actually pass through here without colliding. And so the resistance generally increases. Thermistors actually do the opposite of this. So these are components that we would call negative temperature coefficient. Okay, and this is sometimes abbreviated to just NTC. Okay, so these are usually just called NTC components, negative temperature coefficient. Which means what we're actually saying here is that as the temperature increases, the resistance does the opposite, and it actually decreases. This is the key thing with thermistors, is that they're negative temperature coefficient, so if we increase the temperature, their resistance will actually drop. How does that work? Well, semiconductors have a slightly different material that forms them than resistors do. So instead of being a pure metallic lattice, we will still have what we'd call valence electrons inside the atoms inside the material. And so these atoms will still house some electrons. Okay, so I'm just going to draw the outermost electron level. And this will be true. I'm only going to draw two, but obviously we could extend this lattice to be as big as we possibly wanted. And they have some valence electrons. Okay, and I'm going to draw 4. Again, this is just a number at random. It really depends on what the material is. But as we increase the temperature, so as the temperature increases, what we're doing is increasing the energy of these atoms. Now they could obviously just gain kinetic energy and then start to vibrate, but they could also say that the electrons in these valence shells, what I mean by a valence shell is just the outermost shell, absorb some of that thermal energy. And what that means is that they have enough energy to be ionized. So they leave the atoms. So electrons, let me draw the symbol. So electrons are ionized and leave And when they leave this atom, it means that they're then free. So you can have a free electron, and we know that free electron is in the circuit. So as soon as it has a potential across it, it's going to start being accelerated. So what we actually have now is an increased number. So the amount of electrons traveling around the circuit has increased. Okay, now this means if our current is the charge over time, and we know our charge carriers are all electrons, so the total charge that we have, we could just write as the number of electrons times the electron charge. And if we've increased the number of electrons, that's directly proportional to the current. So by increasing the amount of electrons that are traveling around the circuit, this leads to an increase in current. And we know from R equals V over I that they're inversely proportional. And so if I've increased the current, I've actually decreased the resistance. And so by increasing the temperature, I end up with an effect where I decrease the resistance of this thing. Okay? And this is how both of these semiconductors work. They both work by adding in some type of energy. The electrons absorb that energy. They're then ionized from the atom and are allowed to flow around the circuit, increasing the number of electrons, therefore increasing the current and decreasing the total resistance. So LDRs will work in the exact same way. So LDRs, meaning they're light dependent, so it's just instead of reacting to temperature, they're going to react to light intensity. So these will react to light intensity, and what happens is as the light intensity increases, the resistance decreases. We can't call LDRs negative temperature coefficient semiconductors because they don't react to temperature. There's not really a negative light intensity coefficient, but it would be if that's what we were going to call it. But for now, as long as we know that they behave in the same way as these thermistors, that's completely fine. So what happens is, if we increase the light intensity, the electrons absorb the photons and are emitted and are ionized. And this means we increase the amount of electrons in a circuit. Therefore, we have an increased current and then decreased resistance. Okay, now we've looked at the VI characteristics of these things. We don't really have a VI characteristic for LDRs or thermistors because they will act as just regular ohmic resistors as long as the light intensity or the temperature is constant. But they will react to temperature or light intensity, and we can get a graph for that. And so what would happen is, let's call this temperature here, and this is resistance. We know they're inversely proportional, so we'd say at very high temperatures we have a very low resistance, and at very low temperatures we have a very high resistance. And so what we actually get is something that looks a bit like a 1 over R curve. Okay, so it's a curve because the temperature that we're transferring, that energy, is not going to be a completely linear reaction, purely because it's very hard to have a linear transfer of energy. It's usually as 1 over R or 1 over R squared or something like that. But I could also change this temperature and make it light intensity. It would follow the same graph. Okay, and this is just showing that as the light intensity decreases, we increase in the resistance. As the light intensity increases, we increase the resistance. So this is semiconductors. These are going to be really helpful when we look at potential dividers and the uses of potential dividers, including these. So hopefully this all makes sense, and thank you for watching.